This is a production of Cornell University.
Okay, so erosion, natural process, acceleration by poor management. The process itself, I've mentioned this before, and now we're going to sort of go through the details of it. The first part of it is basically raindrop detachment. The raindrops come down, bang, move it. Transportation, whether it's overland flow or runoff type of thing, and then finally deposition. So let's, this is out of your book, so let's take a quick slide, take a look at this. Basically, when these raindrops come down, they're a force to be reckoned with. Okay, they come down, they're basically acting like bombs. Okay, here's that raindrop hitting. Okay, it hits the ground. Okay, and you can see what it does to that material. Hits it, expands it, blows it up. Now, if this is an aggregate, it's going to take a lot of raindrops to break that up. And the strength of your soil is out. I mean, when we were out in the field at the golf course, you guys remember us talking about rainfall simulator and looking at the raindrops and how those raindrops move through the system? Okay. Well, if these raindrops are hitting these aggregates, certain number of aggregates, the aggregate has a certain resistance. But if I keep hitting it with a raindrop again and again and again, sooner or later that aggregate's going to break up. Okay, and I'll lose the benefit of that aggregate. Okay. Well, all those little particles then can be transported with the water, and ultimately we're going to see deposition. Okay, so here's the Grand Canyon, here's Louisiana. Cool? All right. All right, I throw this in here just to think about this for a second. Okay, what is overland flow? Basically, overland flow is when the water is flowing over the top of the surface. Okay, basically it's a scenario where the delivery of water to the system is faster than the infiltration rate. Okay, if the delivery of water is slower than the infiltration rate, I am not going to get overland flow. Does that make sense? Right? Yeah? So anything that's going to reduce the amount of infiltration will in essence increase the potential, if not the actual overland flow. Cool? All right. So those raindrops coming down, all these little circles here, these oval type of things, these are those structures. The raindrops coming down, they hit that structure. They start breaking it up, and they put it into smaller and smaller pieces. Okay? Those smaller pieces, we start seeing disaggregation at the surface. Okay, what are those smaller pieces going to do? They're basically going to do two things. One is they're going to settle into these cracks. If they settle into the cracks, they're going to be doing what to infiltration? They're going to be decreasing infiltration, right? Because if my pore starts here and it gets smaller and smaller and smaller, as things clog it up, I'm going to have less water moving in, which means I'm going to have more water moving over. Okay? So the first thing they're going to potentially do is fall into these cracks and seal it. The second thing that they're potentially going to do, because they're smaller, is they're going to be carried away. Okay? So I disaggregate. I basically seal the system. When the system gets wet, or it basically creates a coating over the surface, and through the process of the impact, I've basically reduced the amount of infiltration. Does that make sense to everybody? Okay, stage one. Once I restrict that water entry, I'm going to increase the erosion and runoff. And finally, also, now this is the next step down the road, but if I seal that surface, I'm going to impede seeds going in, but I'm also going to impede seedling emergence. So by sealing this system, I'm also reducing the amount of vegetation that's going to be on the system. Okay? All right. Overland flow is favored by ponding then. Okay, if I start sealing, I'm going to start seeing more and more water. And once I start getting that more and more water, I'm going to start seeing the overland flow. Okay, the raindrops seal the surface, and then the rainfall exceeds infiltration. Okay, now, increasing rates of runoff basically produce different or more intense levels of erosion. We start with what we call sheet erosion. Okay, very thin laminar flow of water flowing over the entire surface, basically taking very thin amount of material off that surface. Basically run off in thin, maybe a few millimeters thick sheets. Okay? Then we get, as the water, we get more and more water, this concentration of this water, we start seeing what we call rill erosion, where these sheets start combining into small rivers, basically streams. Okay? The runoff is in many small channels versus one large sheet. Okay? We start seeing deeper and wider channels. As these rills start to converge, like the dendritic system of a stream system, they start converging, we start seeing gully erosion. Okay? Deep, single lane, single wide gullies, channels. Okay? What these things look like, this is out of your book. This is what a sheet erosion, sort of a graphic of it. But take a look here to scale. This is a pencil. And you see these columns here? On top of the columns are pebbles. So what's happening? This gives you a scale. The water is flowing through this entire system. But because the pebble is up here, the pebble has enough weight that it's holding the material that's below it a little bit more stable than every place else. Okay, sort of a pediment design. Okay, does that make sense? Now, when the flow gets a little bit stronger, these pebbles are going to get knocked off too, and they won't stabilize this pillar anymore. That's when you start seeing these convergence of these sheets into smaller channels. And this is when you start seeing sort of the dendritic structure of a stream. Okay, this is a rill erosion. See all these lines, concentration of the sheet erosion into a single line, creating erosion line, erosion channel. Very small. Sooner or later, these things are going to converge, and you start seeing these larger gullies. You can see up here the rills converging into the beginnings of gullies, coming into a very large gully down here. Literally, the dendritic structure of a stream system. Now, if we wanted to quantify this, we use something, right now we use a it's called a universal soil loss equation, okay? And there's problems with this. Most of these are calibrated for very regional locations. In fact, this was designed here at Cornell, the USLE, as well as the revised USLE, okay? It turns out it works fairly well for the Northeast, but from a characteristic sense, from a parameterization, you really have to parameterize these based on the region that you're in. And it hasn't been done for much of the world. Okay? But from a learning perspective, this gives us a good idea about how we can sort of calibrate or figure out where the erosion is and what is causing it. Okay, let's start with the equation. A is basically the sediment load. How much sediment is coming out of a watershed? Okay? And in that watershed, there's a couple things that you should know about. First is R. Okay? And this is basically the long-term average of rainfall as an effect on the landscape. We call it an erosivity factor. Okay? K is the soil's erodibility. Okay? You can think of certain textures, if it's a sand versus a silt versus a clay, if it has gravel in it. You can certainly imagine those different types of materials have different resistance to water moving it. L is the length of the slope that that water is moving on. S is the slope angle. C is whatever conventional soil cover that you're putting in place. Okay, not necessarily conventional, you can unconventional as well. But basically we're looking at some sort of factor that's covering that soil. P is a practice that you're putting in place, usually something like contour tillage. Let's go through a number of these to sort of think about. If you're thinking about managing erosion, these are the types of things you have to think about. Okay, I have to think about how much rainfall is coming. I have to think about the slope and the angle of my slope. I have to think about what type of vegetation cover I have on that landscape and how I'm in fact going to manage that landscape. So let's start with cover, the control of this erosion. Why do I want to put cover in place? Well, primarily for two reasons. One is it literally anchors the soil. It holds it in place. But two is it actually slows the water down. Okay? If I have grass and water is flowing through this system, that grass is going to have a resistance to that water. It's going to slow the speed of that water. If I slow the speed of the water, I slow the energy of the water. Okay, so cover is doing two things. Okay, we also have mechanical solutions. Literally, if I want to contour my landscape, what I do is here's my original slope. Okay, I literally cut, fill, cut, fill, cut, fill. What am I doing? Well, I'm changing my slope. Yes, in part of my slope, I'm making it dramatically steeper, but I'm also making a huge chunk, I'm making these nice and flat. So if I change the angle of my slope and the length of my slope, I'm going to change the scope that water can run and therefore reduce the amount of energy that water has when it's flowing. I also have a lot of different types of tillage practices that I can take into account. I can use grassy waterways. Okay? In essence, I'm literally using the cover of my crop, in this case grass, to hold the soil and stall the water. Okay? Now, I can certainly run it along contours, which makes sense. If you think about it, if this is my slope coming down here, this is my slope. If I don't have anything on this, the water is going to flow all the way down this, and it's going to have a lot of energy in there. Now, what happens if I put some sort of barrier in there? Okay? And let's talk about tillage practices or strip cropping or something like that. What happens if I put in corn here, followed by grass, followed by corn, followed by grass, followed by corn? Now, the corn doesn't do a lot to slow that water down. Okay? I also have grass up here. Okay? But this grass stalls that water a lot. So that by the time it gets here, it's moving very slowly. Hits this corn, it's going to pick up speed, but because it started with such slow speed, it's not going to have a lot of erosivity in it. Okay? Hits the grass again, slows down, hits the corn again, and so on and so forth down the system. Does that make sense to everybody? Okay? So how I, in fact, plant my field has a huge impact on the erosive nature of that field, or the hill slope that's in that field. I can certainly put grassy waterways in there. I can certainly put strip cropping in that you saw here, but I also can put in conservation tillage, where I, in fact, when I'm done with that corn, I don't clean it totally out. I leave the stubble behind. It acts, it may not be super effective, but it acts to a certain extent to help reduce the amount of water that's the energy of that water that's moving over that soil. Okay?
This has been a production of Cornell University, on the web at cornell.edu.